Hey everyone, DeepSeek is back with another open source drop. Their freshly released paper is called DSpark, and it pushes the cost of generating tokens with large models down even further. So today, let's dig into it. As you all know, now that agents are very popular, token usage has exploded, which makes the inference faster and cheaper, more valuable than ever. And from the title alone, we can already tell the paper is about speculative decoding. So that's where we all start. What is speculative decoding? So alongside the large target model, we keep a much smaller model called the drafter. Given a prompt, we let this small drafter quickly propose several tokens, called draft tokens. And because the drafter is small, this process is cheap. How the drafter proposes several tokens is something we'll come back to later. Those draft tokens then go through a single forward pass of the target model. That pass gives us the logits and then produce log props at every position, which indicate the next token's distribution. And with this target model distribution, we can verify the draft in one shot whether the big model actually would have produced these tokens. In the example here, we have three draft tokens T1, T2, and T3 prime. T1 and T2 are accepted while T3 prime is rejected. So why is this faster? Essentially, it makes the target model more compute bound. Verifying these three tokens in a single forward pass is far cheaper than generating token 1, token 2, and then token 3 one at a time, the autoregressive way. That's where the speedup comes from. So how does the drafter actually generate those tokens? There are two main approaches, autoregressive versus parallel. Let's take the autoregressive route first. The representative works here are DeepSeek's MTP and the Ego series. DeepSeek MTP was proposed in December 2024, where it first showed up in the DeepSeek V3 technical report. Originally, it was not an inference trick, it was a training trick. During training, the model doesn't just predict the next token, it also predicts the second and the third tokens ahead. In other words, you are forcing it to learn a harder task. And they found that once a model can predict several tokens ahead accurately, its single next token accuracy improves as well. At inference time, the MTP module can simply be thrown away, which is why people call it training only, but you don't have to throw it away. You can keep it around at inference and use it for exactly the kind of speedup we just described. Since MTP's actual layers are small, drafting with them is fast. On the other hand, the work that really made multi-token prediction about inference speed and did it earlier is the Ego series, including Ego 1, Ego 2, Ego 3, and the recently released Ego 3.1. We won't get into the details, but here is a key picture. Ego generates one draft token based on main model's activations and embeddings, feeds some information back in, generate the second draft token, feeds it back in again, and generate the third. So it's still autoregressive decoding, one token at a time. Just a fast version of it. This picture is Ego 1. It generates a static token tree and uses next feature prediction. Future Ego series change the loss function, the tree shape, and the feature fusion. The other approach generates all the draft tokens in parallel. The notable examples are the earlier Medusa work and the more recent DFlash. As you can see, Medusa's heads are independent. One predicts the next token, another the token after that, another the one after that. The upside is obvious. Propose several draft tokens at once, it's fast. And the downside is just as obvious. There's no causal link between those draft tokens, so the later positions are hard to get right. Now we have seen the Medusa picture, let's zoom in on DFlash. DeepSeek's new paper DSpark builds on the DFlash architecture as one of its key components. Let's start with DFlash drafter's inputs and outputs. Say our prompt is diffusion is good. It goes through one forward pass of the target model, which produces a bonus token 4. So now we have diffusion is good 4. We take the embedding of that bonus token, also called the anchor token, and feed it into the drafter as its first input. Now suppose we want to predict the next 3 tokens. We add the mask embeddings for those 3 positions as inputs too. But that's not enough on its own, because all we have fed in so far is the last bonus token 4. We still need to mix in the context from the target model, which is diffusion is good. And that's what the 3 blue blocks on top are for. We'll get to what they actually are in a bit. The output of the draft is the 3 tokens on the right. In this example, they come out as speculative, decoding, and the end of sequence token. Back to the inputs in detail. DFlash uses a technique called context feature fusion. It takes the hidden states from the target model and runs them through a projection. Where do these hidden states come from? They are uniformly sampled from the target model across the target model's steps. If you want 3 of them, for instance, you pull them from the layer 1/3 of the way down, the layer 2/3 down, and the final layer, those hidden states or activations. In this formula, we pull the hidden states from M layers, H layer 1, H layer 2, up to H layer M. Multiply each by a shared projection weight WC, and then normalize them. Now we have got the semantic information from M layers in hand. So how do we use those M features? DFlash injects them into the Kiwi cache. As this line says, the target model features go straight into Kiwi projection, and it happens on every draft model layer. Let's go back to the architecture figure. You can see these features are injected into every layer. And here is the exact formula for the Kiwi injection. Each context is the M hidden states from here. We multiply it by a weight matrix WIK, and then concatenate the drafter's own hidden states after it. So that's a key tensor. And this is the same for the value tensor. So in this figure, the top half is from the context feature, and the bottom half is the drafter's own states. With KV in place, we run the attention calculation. And the attention is bidirectional, which makes it more accurate than causal. And since your output is not causal, we can do bidirectional. The attention layer and then followed by the MLP layer. Finally, the output. At each position, we get the next token logits, then get the log props, we sample from the log props, and out come our draft tokens. Okay, that's all the background. Let's pull it together. We have 2 styles. One is autoregressive, one is parallel. Autoregressive is slower since it emits tokens one at a time. It's accurate because each later token is only guessed after the early ones are fixed. So it's an easier job. The parallel style emits many tokens at once. It's fast, one forward pass, and every draft token is out. But the accuracy suffers, especially towards the end of the block. DeepSeek's new work DSpark tried to marry the two and take the best of the both. Before we get into DSpark's architecture, let's figure out how much speculative decoding can actually buy us and what governs that. With speculative decoding, every decode step split into 2 phases, drafting and verification. So the step time is just drafting time plus verification time. Now what we really care about is the average time per token. For that, we need one more metric, toll, the average numbers of tokens accepted per draft and verify run. Divide a step's time by toll, you'll get the average time per token. DSpark goes after all 3 of these levers. To reduce the drafting time, in DSpark, the drafter spent most of its time in parallel drafting unit. But as we said, parallel drafting is less accurate. So to keep the accepted length toll high, DSpark has a lightweight autoregressive module that corrects the logits the parallel drafting produces. And to reduce the verification time, DSpark doesn't blindly verify every draft. For the drafts that look unlikely to be accepted, it just skips them. No verification, no wasted time. So each of these is not new idea, but DeepSeek gracefully combined these together and did a very good engineering work. Alright, enough setup. Let's see DeepSpark end to end. We start with the target model. Assume the prompt is token A, B, and C. After one forward pass, the target model produces a bonus token D, or the anchor token. Then D plus 3 masks become the input. That input runs through the parallel drafting unit, and for every drafting position, it outputs logits, which indicate the next token's distribution. These logits are then fed into an autoregressive unit, which rolls out tokens E, F, G, and H in sequence. At the same time, each token gets a score for how confident we are it will be accepted. The scores go to a scheduler, which decides which tokens are actually worth verifying. Here, scores C1, C2, C3 are high, so we verify those. C4 scores low, so we drop it. There's no point spending verification on it. So EFG has off to verification. EF are accepted, G isn't. At that point, we emit a bonus token G star, and the whole 1, 2, 3 cycle repeats. Now let's walk through these three pieces in order: parallel block, the sequential block, and the hardware-aware prefix scheduler. The parallel block is essentially the D flash we covered. It is used as the backbone with a small tweak. In this flash, you feed one bonus token plus gamma masks and predict on those gamma masks. In DSpark, we let the bonus token or the anchor token serve as the first prediction position. So the anchor plus the remaining gamma minus 1 masks gives gamma draft logits in total. In the sequential block, we want to add a prefix-dependent transition bias. What does this mean? It means a token's probability should depend on its own prefix. We know which bonus we have, we know the early drafts. Given all that, we generate this draft and we want to know how likely it is. That is the transition bias. So when we produce the draft logits, the logits as position E, F, G, and H, we blend it in the backbone's logits. Look at this formula. V is a token, and the UKV says at position K, the parallel backbone already assigns some probability to the token V. We take that and add the transition bias on top, and that sum becomes the final score. Then we run a softmax. So in essence, the sequential part is conditioning on x1, the bonus token, and x less than k, or previous drafts. How is this BK bias implemented? Two options: Markov head and an RNN head. Recall how a Markov process works. The next state depends only on the current states, not the ones before it. Here, that means the token at position k depends only on the token at k-1. That's a simplification, of course. The true xk depends on x0 and every previous draft. We are deliberately dropping the older context and keeping just a single preceding token to make the next prediction. With that simplification, B is just a V times V matrix, where the first V indexes xk-1 and the second indexes xk. So given any previous token next token pair, the matrix tells us how likely that pairing is. That's how we model the sequential signal. We swap the simplified BK for the full BK. The sequential output then fuses with the parallel output. As we noted, the bulk of the drafting time should live in the parallel block, which means the sequential block has to stay cheap. How? DeepSeek shrinks that V times V matrix with a low-rank factorization. B equals to W1 times W2, where W1 maps from a V down to a smaller rank R, and W2 maps back from R to V. By default, R equals 256. With this, W1 becomes an embedding lookup table. Every token in the vocabulary gets a length R embedding, and W2 maps that embedding back to logits, since it restores the V dimension. Now, you might worry that throwing away the older context makes the sequential part less accurate. That's why we have an alternative, the RNN head. It maintains a recurrent state that compresses the entire prefix history. In practice, the gap between these two is small, partly because we still carry plenty of thematic signal through the parallel path. The experiments later will show just how small the gap is. In summary, we have a heavier parallel block plus a lighter sequential block. They work together to produce logits that are both fast and accurate. Now for the verification. As mentioned, every draft token K gets a score for how sure we are that it is correct. This score, CK, is a probability that draft K is accepted given that draft 1 through K-1 were all accepted. How do we get it? We tack on a linear layer to turn it into a score and push it through a sigmoid to land in the 0 to 1 range. The projection layer takes two inputs. The backbone's hidden states at position K as the Markov embedding of the previous token. During training, we supervise CK against the analytical computed acceptance rate. We didn't walk through that computation, but it does have a clean closed form expression. And DeepSeek treats this score very carefully. They add a trick called sequential temperature scaling. The motivation is that neural networks tend to be overconfident. Their scores run hot. So this calibrates the scores back down to something trustworthy. Okay, that covers how the scores are produced. Now how do we use them? Prior work basically picks a threshold, and it's a static threshold. If the score is larger than the threshold, we verify it, otherwise we don't. But this misses something. The cost of verifying a token isn't constant. It depends on the system's current load, such as batch size, context length, and those will affect your verification overhead. Take batch size as an example. The larger it is, the more compute bound the system becomes, and the worse the verification gets. Why? Because once you are more compute bound, throughput is essentially fixed. So every extra token you verify directly costs you more time. We won't unpack exactly how they set the throughput from the system load. The takeaway here is that DeepSeek frame it as a global throughput optimization problem. With all the main modules covered, let's touch briefly on training. There are 3 losses and all 3 are intuitive. The first one penalizes getting the predicted token wrong. The second one keeps the target model and the draft model's distribution close. And the third acts on the confidence score. Each of these 3 are weighted by draft token position. We will skip the details, but the guess is that earlier positions get more weight. So how well does all this train up? Let's look at the numbers. Across 3 Crane models, DSpark beats Eagle 3 by about 30%. And beat DeepFlash by around 16 to 18%. And on DeepSeek's own models, V4 Flash sees a 60 to 85% speed up, V4 Pro sees 57 to 78%. Let's look more closely. Notice that DeepSpark is 30% faster than the autoregressive Eagle 3, but only 16% faster than the parallel DeepFlash, which tells us the parallel DeepFlash already brings most of the speed up. Why? Look at these 3 figures from the paper. The x-axis is the draft position and the y-axis is the acceptance rate. Blue line here is the parallel DeepFlash. At the very first draft token, DeepFlash is way ahead the autoregressive Eagle 3, but it falls off more and more at later positions. All 3 plots tell the same story. The reason traces back to the architecture. In an autoregressive drafter like Eagle 3, drafting is slow, so you are forced to keep the drafter smaller. In this paper, Eagle 3 uses a single draft layer, while DeepSpark and DeepFlash both use 5 layers. Now think about position 1. For the very first position, autoregressive versus parallel makes no difference at all. There's no previous draft to condition on. And since DSpark and DeepFlash each have a 5-layer drafter, they are simply more capable, so they win at position 1. At later positions, pure parallel DeepFlash drops off hard, while DSpark, thanks to its sequential stage, holds a much smaller acceptance rate. So layer count matters a lot. Let's isolate its effect. In this figure, blue dots are DeepFlash and the green dots are DSpark. The x-axis is different datasets, and the y-axis is tau, the average number of accepted tokens. The takeaway is that more layers means longer accepted length. Look at the first dataset. Here is 1 layer, 2 layers, and 5 layers. The more layers, the bigger the number, and it holds on every dataset. The second takeaway is that the biggest jump is from 1 layer to 2 layers. Going from 2 to 5 buys you much less. And the final takeaway is that a 2-layer DSpark already beats a 5-layer DeepFlash. And again, this holds across all datasets. Another big factor in the accepted length tau is how many draft tokens we propose, or the proposal length. Here are 3 plots. The x-axis is how many drafts we propose, the y-axis is how many we accept. First, unsurprisingly, every curve is monotonically increasing. Propose more, accept more. Second, as we propose more tokens, the gap between DSpark and DeepFlash widens. That makes sense. DeepFlash is parallel, so the further into the block it goes, the harder it gets. DeepSpark, on the other hand, still has its sequential part, so it can lean on the early tokens to make better predictions. Last, the relationship between the proposal length and the drafting time. Again, blue is DFlash and the other two lines are DSpark. As you propose more tokens, drafting time does climb, but next to verification time. Verification is still the heavyweight, and this curve grows sublinearly because the x-axis is in log scale. So that's the whole paper. Let's head back to the architecture figure and sum it up. It fuses the parallel and the sequential decoding styles. So on one hand, the drafting is fast, and on the other, thanks to the sequential block, it's also very accurate. That's a really clever combination. On top of that, DeepSeek validated the technique in live production, where it replaced their previous MTP. That's it for this video. If you enjoyed it, drop a like, save it, and share it around. See you next time.